So the fuel models are a little tricky because early on, the original developers never wanted this fuel model complication that we have. They always wanted 4 or 5 fuel models for NFDRS, but they got they had a committee, steering committee. How many people ever worked with steering committees? They're like, well, 4 is not enough. Well, why isn't 4 enough? 4 is not enough because you don't have my name. You don't have my fuel type name in your 4, so therefore your system is junk and I'll never use it. So they went back and they said, well, how many do you want? They said, well, how's 20 sound? So they made 20 fuel models, but you know what they did? They took the 4 or 5 that they wanted and they modified them 4 or 5 times to get 20 models. So what they ended up doing is adding complexity for zero gain. Because when we started out this discussion, we said, how do we apply fire danger? We apply it in a relative sense by knowing what's a normal range of values for a particular place and comparing today's values to that range of values and expressing them as a percentile, right? So here's what happens. If you look at these things over here on the left from Jimenez, you looked at those graphs, you'd be like, those things are totally different. Wouldn't you? I would. But remember how we apply fire danger. We don't care about absolute values, right? These things are plopped on the same graph and fixed based on this range of values. If we just take this bottom one and move it to the right side and let it have its own range of values, normalize it its own way, we get this over here. These are I, J, and K. These are basically for 2 of the slash fuel models that are in NFDRS right now. And what it means is that if you don't care about the magnitude, the seasonality of these 2 indices is identical, meaning like R squared of 1.0 kind of identical. So what they did is they said, fine, I'll give you 3 slash fuel models. They started out with the one they wanted, and they added proportionally more loading into each category to give you a different fuel model. So you got 3 different slash fuel models that all tell you exactly the same thing. So that's what we're going to fix. This is just an example of what this looks like. We went, picked stations from all over the country, ran it for ERC, fuel model G, actually for every fuel model. So we have ERC for 20 fuel models. And then we just looked at the correlations between each unique pair. Some of them were real similar. Some of them weren't so similar, but they all clustered into groups. And this is just an example of I and K, who had a correlation of 1.0, and then G and H, which have always been pretty darn close to each other. But then you see some that are appreciably different. So G and C, correlations are like 0.68, F and T, 0.67. But we can take that matrix of correlations and pump it into this display mechanism that says, show me the groups that are truly unique from each other and show me the ones that are most correlated. So that's what this figure is the lines here, right here. If you follow this across, that is the correlation between these 3 fuel models. So I, J, and K have a correlation between each other of 1.0, meaning that they're absolutely not unique. The farther you go up in these lines, the less similar the groups get. So, but what you see over here is that these grass and shrub models cluster together, and 0.85 is the magic cutoff for not being correlated with each other, basically being independent. And what we found is that these things can be, with a little bit of latitude, broken into 5 fuel types: grass, grass shrub, timber, brush, and slash. And the other thing that we can do now is we can pick a representative fuel model from the Scott and Bergen 40 fire behavior fuel models and not have fire danger fuel models at all. We just pull one that's representative. So that's what we did. So we used the GR2, GS2, the Shrub 9, Timber Litter 1, and the Slash and Blowdown 1 models from Bergen, and we combine that in with a 1,000-hour fuel loading and a drought fuel loading, and then we've got our fire danger fuel models that are already being taught to firefighters in their early 90 fire behavior series. We don't have to teach fuel models at all for fire danger. That's kind of nice. We tell them we use these fuel models and we add this 1,000-hour loading and you're done. So interestingly, I was reading that Bergen paper that I talked to you about earlier, our Deeming paper, and he said two things. He said the standard fire danger rating models will be a subset of the fuel models used for fire behavior prediction and planning. I don't know if this was subliminal or not, but we did this, and then I read this, and this was written 30 years ago. That's what he said we should have done. So he'll be happy. And then other things like the live fuel moisture models will certainly be improved, as will the dead fuel moisture models. This came from that 1987 paper that I started out with. It's crazy. We're finally catching up. Things people have known for decades. So there's a crosswalk table to get you across. Generally, it should be fairly straightforward to apply to translating it. In Fire Family Plus, if you go into the NFDR calculator, there's a little fuel model button down at the bottom. You can pull one of the new fuel models down. They are lettered VWXYZ for the new fuel models. And you'll get a table like this that'll tell you the same thing we had before: 1 hour, 10 hour, 100 hour, 1,000-hour loading, herbaceous woody loading. There's a drought fuel loading, which I'll talk about in a minute. Things like surface area to volume ratios, heat content, moisture extinction, fuel bed depth, wind adjustment factor, and the maximum spread component. So probably not a big impact anyway, because we weren't using all those fuel models. We really weren't. And if we were, we could have used another one and had the same or better system anyway. Talk about some of the minor changes to NFDRS that also you may see crop up. They probably aren't going to be that important for you, but some places they might be. One of them is, how many people have taught 491? Probably a few at least, right? How many people remember the dynamic load transfer lesson in the live fuel moisture? Holy crap. I've taught that thing like 30 times, and so now I'm done. Because it is really, really complicated and unnecessarily complicated and not all that helpful.
So you just threw that out there. You said it's done. So then I have a question. So here we are with 2016. What is the status on, since I am an instructor of 491, getting that updated?
So it is updated, and they have an alpha course that's going to be taught soon, like in the fall, I think. And that they're going to teach the alpha course in the fall and then the beta and right in January-ish in the Northern Rockies for the new course. And the new course will be available for other peeps to take up, and it will have all of the NFDRS stuff built in. The new NFDRS 2016 changes, and the whole structure of the course has changed to be more about scenarios, more about learning. Because one of the benefits of simplifying NFDRS is that we can now use. I'm out of the box. This is really hard for me. We can now use the time that we gained from the simplification in 491 to focus on applications. How do we use it? How do we learn about what does this tell me about my fire activity, and how can I incorporate that knowledge into day-to-day fire business? So the scenario-based learning will be a move towards that. So drought fuel loading is replaced by a simple GSI function that does the same thing. We'll look at that. Talk about the drought fuel loading separate, which is driven by KBDI, moisture extinction, and some site-specific parameters that you can change if you need to. And we'll talk about why those are. So essentially the way the curing function works is that we already talked about GSI. And inside GSI, we know that we define a green up threshold so that when we go above that threshold, the plants are greening up or reaching full green. And when we drop below that threshold, we assume they're fully cured. The same thing works for woody plants, which go from dormancy to green. That works for herbaceous plants, which go from cured to green up back to cured again. The process is the same, but we only treat curing as a way to reflect the grass, the ratio of live to dead in grasses, basically. And we use GSI to do that, such that we have a loading in the herbaceous live loading and the fine dead loading, and all it does is move loading back and forth. So when you're fully cured, all the loading that would have been in the live herbaceous category just gets added to the 1 hour. And then as you green up, some of that fuel gets taken out and make green in the model until when you reach GSI 1.0, which is fully happy plants, you're at the maximum loading of live fuels. And that can move back and forth throughout the season based on GSI. So this is just kind of graphically what that means, is that when you're below the GSI threshold, this line, that's 0.5, everything below here is when you're fully cured, which means you have no live loading, and all of that loading is added to the dead loading until you reach the green up threshold. As you go with a GSI, increasing GSI means you're getting greener and greener. So as it goes up, your live loading goes up, your dead loading comes down, and there basically all it does is add this fraction to the dead fraction when based on GSI. So it's very similar to the way the dynamic load transfer worked before, but in this case, it's just a straight function of GSI, and it's literally just moving loading back and forth as a function of green up and curing. We can prove that, again, by looking at our handy dandy little calculator. So if we go to Fire Family Plus, again, maybe, doop-a-doop, and be patient and don't open it up twice. Crash. And open up our calculator. So the simplest way to look at that is just to look at the grass fuel model. So if we pull up V for fuel model V, which is our grass model, if we want to know what's in there, we can go to fuel model parameters and pull that fuel model up and add it to the table. And it'll tell you some valuable stuff here. One, it tells you that this is the simplest fuel model on the planet because it only has 2 loadings. It has a 1 hour dead loading and a live herbaceous loading. And all the other loadings are 0, which mean that for this model, it doesn't matter what the fuel moistures are for any of those other things because the loadings are 0, and the only fuel moistures that are used to calculate this model are the 1 hour and herbaceous. Does everybody know what a weighted average is? Do you know how that works? Or this is kind of helpful, I think. And that is, you think about it this way. So if you wanted to get, if you wanted to have, so it worked the same way SIGs work, right? So with SIGs, you can have, say, 3 stations, and you can give one station more weight than the others, right? The same thing explains how fuel models work, because fuel models are basically just a way to weight the individual fuel moistures for the index that comes out. So imagine just having three categories, like a fine dead loading, a coarse dead loading, and a live loading. And you say, let's make this one, so the fine dead loading, let's give it a weight of 10. And let's give these others a weight of 1 apiece. And they each have a fuel moisture associated with them. So maybe the fine deads are like 6, the coarse deads are like 15, and the lives are like 60. To figure out what that weighted average is, all you do is multiply the number by the weight, and you divide the result by the sum of the weights. So, which means that in this case, you would do, it'd be 60 times, and 15 and 60, and you divide that by 12. The reason that's important is because with a fuel model like this, any time a number is 0, it means that it doesn't matter what that number is to the final calculated value. So these weights, anytime one of these weights becomes 0, whatever that fuel moisture is irrelevant to the final number that we would get out. So in this case, you know, if we had, what's that, 120, it's 135 divided by 12. Who's got that calculator? What was that, 11.25? I like it. That's about right. So let's just say that that's the weighted fuel moisture. And what you'll see is even though the live fuel moisture was 60%, the weighted fuel moisture was 11. And that's because we gave 10 times more weight to this 6% than we did to this 60%. If we take the same idea and we say, well, what if we set this coarse wood to 0? But for some reason, the model says that the moisture content is a 1500%. 0 times 1500, 0. And then these two say the same. And now our sum of our weights is 11. So then our average is 120 divided by 11. What's that? What is it? 10.9. So 120 divided by 11 is 10.9%. So regardless of what this number is here, it has absolutely 0 bearing on the output. That's exactly how indices are calculated in fire danger. Is the fuel moistures come in here, all 6 of them, they get a weight based on one or the other things. One can be the loading, the other can be the surface area to volume. Either way, you get a weighted number out that's heavily influenced by the magnitude of their weight. It's the very reason that ERC Fuel Model G works, because it has a weight of about 16 to 1 of all the other size classes of fuels. It's the reason why a grass fuel model like this works regardless of what the 1,000-hour fuel moisture is, because it just ignores it. So there's your little tidbit. But so here we have an example for a grass fuel model. But if we calculate, keep everything the same, 3 and 30%, right? And we calculate. And we look at spread component. Spread component is 108. If we increase the GSI, who's my record keeper? Would somebody write 5 numbers down for me? Awesome. So if we have the GSI set at 0.5, what does that mean? Remember that 0.5 or below is what? Dormant, right? So that means that the grasses are fully cured and all the loading in this case, if we go back to our example, it means that our 1 hour loading is 1 plus 0.1 or 1.1. And there is 0 loading in this herbaceous category. As we increase that number, so we go from 108 to 0.6 and hit calculate, the spread component goes to 97, 0.7, calculate, goes to 86, 0.8, calculate, goes to 72, 0.9, calculate, goes to 54, and 1.0, what's 1.0? What does that mean? Full maximum greenness? Happy plants. That's what that means. Happy plants. We like happy plants. The spread component goes to 0. So if we plot those quickly, call them off, 108.
108, 97, 56, 72, 54, 0.
And you see the effect of GSI on spread component. It looks like, what is that number? I must be list X6. $86. There we go. Oh, look at that. No weighted average there. There we go. So again, like I said, this tool, the calculator, can be used to learn. And it can be used to do things like see what the impact of GSI and load transfer are on spread component. So it should be fairly intuitive that as GSI goes up and things get greener, grass spread rates are repelled by the higher moisture content of live fuels. That's how fire works. To some point where fires won't spread. And they stop because it's too green for fire to propagate through said dead fuel, live fuel combo. Okay? So use it. Let it help you learn. If you have any questions, and we've done other checks looking at just grassland curing and what GSI relationships are. These are satellite observations for grasslands in North Dakota, but yeah. Yeah, no, it's so now that we are on the home stretch of, like, with Fire Family especially, like getting a very stable version, we can start cranking through that stuff fast. My thought is that is twofold. We're going to start actively using the blog on the NFDRS2016 site. You can write little short stories that are very compact. I'm shooting for no more than 3 to 5 minute nuggets. And we'll also start a series of basically like 30 minutes or less once a month webinars that are then recorded for YouTube. So you can get the tips and tricks more about, rather than having to read it, you can listen to it and follow along and do some stuff too. So yeah, and Chuck's worked through all of that already, so y'all have that before you leave. Yeah, so a lot of those things will kind of follow along. So I'll skip the math on this part, but generally it's exactly what I just told you, is that as the GSI goes up, the live loading goes up. As it drops down to less than the green up threshold, everything below that is considered dead 1 hour fuel. That's all you really need to know. Drought fuel loading is something that I struggled with keeping, but we kind of need to, because NFDRS needs a way to incorporate true drought that persists for longer than 4 to 6 weeks. The KBDI drought-based drought fuel loading that was added in the 88 system is a good start, but KBDI doesn't work everywhere, and it doesn't work the same everywhere. So we kept it, and it's in there by default. You can't turn it off, but it doesn't hurt anything. And it gives us a new hook to add a better drought index in the future. So we have the method to incorporate it into fire danger, and that's driven by an existing drought index right now, which we already have a new version of KBDI that's more generalized, that's driven by a full water balance rather than the kind of half made up way that it does now. It gives us the same answer with the same scale, but can be applied across the whole country. We just have to test it. So, but what it does is as the KBDI goes above 100, that's that line right there, it just adds more fuel into each category that has loading. And we'll just do a quick example so you know what that looks like. If you ever wonder what Fire Family Plus looks like on the inside, this is it. And it's really, it seems a little intimidating, but what I want to draw your attention to is just this W right here. So that is the drought fuel load corrected 1,000-hour loading. And all it is a combination of the initial loading plus some the 1 hour fraction of the total dead loading times this little factor of KBDI. And then this is just the incremental drought, the drought loading that gets added to it. So it's just a simple math thing where it says if I have loading in this 1,000-hour category, I'm going to take some fraction of my drought loading, my drought fuel loading, which is specified in the fuel model, and I'm going to add it to that 1,000-hour loading based on how far the KBDI is above 100. And all that really does is shift the scale up and down of the ERCs. It doesn't actually change the seasonal dynamics very much. It's just sort of like it makes the ERCs higher during periods of drought, which is fairly logical, but it's as I said, it's not generalized, not as generalized as it could be. Yeah. Yeah, so when you run an analysis, the same thing that's done in real time is applied historically. So when those things shift up or down, it's in Fire Family already. And it's doing that in the background based on the KBDI for that day. So historically, your range of conditions is already incorporating those shifts. So, yeah.
Hey, Matt, does that only apply to Y and Z that have 1,000-hour fuels in the profile to begin with?
No, it applies to, so let me show you how to find that out. That's a good question. We're going to go back to the NFDRS calculator. And we're going to pull up fuel model parameters. And we have V here. We're going to add W, X, Y, and Z. And then we're going to scroll down here and we're going to look at this column right here called drought loading. That drought loading, you will notice there's drought loading in 4 of the 5 models. So there's none in the grass model. But essentially, these are in tons per acre. So it means that at the highest KBDI of 800, 5 tons per acre is added proportionally to all of the dead classes that have loading. So in this case, in Y, a little bit will be added to 1, 10, 100, and 1,000, and the total will add up to 5 tons per acre. So the only one that won't have it is the grass model, and the other ones don't have very much of it, so it doesn't have that big of an effect anyway. But it's there, and gives us a way to improve it in the future. So let's see if we can, I wonder if we can actually do this. I believe we can. We're going to work through this. It'll only take a minute or two. We do need to know some things. Here, for our recorder, who's the recorder? Who wants to do it now? It's easy, I promise. Awesome, thank you. We need to write these down. These are our loadings for 1, 10, 100, and 1,000. That'd be 2.5 tons per acre, 2.2 tons per acre, 3.6 tons per acre, 10.16 tons per acre, and the drought fuel loading is 5. And then we'll come back to here and we'll say our example is how much drought fuel loading is added to the 1,000-hour loading when the KBDI is 650. We come back to this handy dandy little very confusing thing, and you see how a model works. The model says we want this number right here, W1000, which means we have to start with the initial W1000, which is the loading that's specified in the fuel model, which is like 10.16. So we write down 10.16 plus 10.16 divided by the total loading for dead. W tote D is the total dead fuel loading, which is those 4 numbers added together. Got a calculator? So it was like 2.5. So our W tote D, which is the total loading, is 18.46, right? And we say, so then we're going to add, so W1000 over W tote D is just the fractional loading of 1,000-hour fuel moisture relative to the total loading. If you take temp, so KBDI minus 100, so that would be 550, times the drought unit, and the drought unit is just calculated as our drought fuel loading divided by 700. So it'd be, we do that, so let's see. 5 divided by 700 is the drought unit. What that drought unit is means for every 1 point change in KBDI, we add that much loading to total loading to the fuel model. So when you go above 100, it's 5 divided by 700. So if you do that, let's do this real quick. So it's 550 times 5 divided by 700. $3.92. So at that KBDI, there is a total new loading of 3.92 tons per acre. But we're going to proportionally allocate that to the 1,000-hour fuel moisture, which is our loading, 10 point, whatever that was, 10.16 divided by 18.46. .55. So that means that we add 0.55 tons per acre to the 1,000-hour loading when the KBDI is 650. And the balance is added to these other 4. So you'll notice that their proportional loadings are expressed relative to the total. So they all add up to 1, basically. The proportion will add up to 1. Make sense? If one of those doesn't have a loading in one of those categories, back to our weighted average example, it's basically ignored. It has a loading of 0, which would mean that this number, 0 divided by anything, is 0. So, got it? So there's some other things that we did. We found a few things along the way. So for example, if you run NFDRS, calculate adjective rating in Florida, for the majority of the state of Florida, you will never have a single day where the adjective rating is extreme. It doesn't happen because the original developers made a mistake. They made a mistake by assuming that the spread component is comparable between places, and it's not. So spread component, just like energy release component or anything, is determined by the climate of a place. Wet, cool places have naturally lower spread components, particularly if it's not as windy, than hot, dry, windy places. If you look in the fuel model, there's a little hidden parameter there that we don't ever talk about called the maximum spread component. So this has been in existence before. If you pull up the fuel model G, it'll have one too. The maximum spread component is the spread component above which all fires are reportable fires. That's the book answer. But what the model does is it uses that maximum spread component to calculate ignition component. Do we remember where ignition component is used in a public communication tool? In adjective rating, all the time. And we'll show you that just to clear it up in a minute. But if you have a place where the spread components never get up to the SC max specified in the fuel model, you will never get an ignition component high enough to push you into an adjective rating of extreme, regardless of what the conditions are. So in the future, we're going to get rid of all of that stupid crap because it doesn't help. That the assumption somehow that ignition component should be tied to adjective rating is flawed in a number of ways. So there's pretty much zero reason why you wouldn't just use a straight ERC under most conditions to define an adjective rating range. This combination was something that was developed. It works fine in the West because places that are hot and dry and windy enough always have areas and times where those ignition components push up into values high enough to give you an extreme adjective rating. But it absolutely doesn't work in the humid South. So we made that parameter selectable. You can calibrate it. That's pretty straightforward. Instead of having it fixed for the same, just because you pick this fuel model and apply it across the whole country, you are allowed to go in and calibrate it if you need to. And it's important because there's pieces that really, where that's going to matter. Also, moisture extinction for the same reason. So one of the things that Bergen did in the 88 system is change the moisture extinction from whatever it was in the 78 model to 40%. And we carried that over to just a flag called humid. And all a humid flag does is reset the moisture extinction that's defined in the fuel model, which you can see it right here. This moisture extinction value says that 15% means that if your weighted fuel moisture for that day is above 15%, your index is 0. That's how that works. It's the moisture content above which fire doesn't spread. It's part of the Rothermel logic. Whether it makes sense or not, we'll talk about that over adult beverages. But why does it matter? Some of this stuff really matters for the evaluation too, which is what we're trying to get into now, is because in WIMS, there's a lot of magic in WIMS, and if you're not careful, it can be doing things that you're not real clear about. How many breakpoints do we define in WIMS for an index, for something like staffing or adjective rating? 2. 90th and 97th are common, or sometimes it's 80th and 95th. They're usually derived from climatology. For a particular fuel model in WIMS, you go in and you put those 2 values in. The way WIMS uses them is the magic part, is that it goes in and defines a computed class level, 0 through 9. It takes that staffing index and calls the small one low and the big one high, and then it computes out 10 classes from those 2 breakpoints. It makes 10 classes by doing this. So it says anything up to staffing index low divided by 8, so your 90th percentile, for example, is in the computed level of 1, and it does that all the way up to here, such that 9 is anything that's greater than your upper breakpoint. And to condense that down, we also tell it how many staffing classes we want. So we say we want 5. It takes these groups and collapses them or combines them into different categories, such that 5 is always above your highest percentile, but 4, in this case, for 5 staffing classes, is a combination of this computed class 8 and 7. So the staffing index high, all the way up to your highest breakpoint, down to the average of your high and low breakpoint. So somebody totally made this crap up. That's what you need to know. But it really matters. And it kind of still works. But the intent is we take 2 numbers and rather than having, for whatever reason, rather than having all of your breakpoints put in for your staffing classes, it takes those 2 numbers and turns it into the number of staffing classes that you need. The reason that's important is because we go from staffing class to adjective rating. So that means that over here, we have these things. So whatever staffing class you fall into defines this y-axis. The x-axis is determined from the ignition component. And you can see right away that if your ignition component never gets above 65, you will never be in extreme fire danger according to fire danger rating, ever. So we got to fix it. This is what WIMS looks like. If you do an edit station in WIMS, and you go in and you'll see it doesn't have the new fuel models loaded, but this is the new WIMS with stuff in there. You come over here, you see this, staffing index breakpoints. DC is the number of decision classes you want, or the number of staffing classes. So if you go back in this example, that is 5, isn't it? It would say that we're here and that we're going to have staffing classes of 1 through 5, basically, generated by the system. And we're going to do that with a 90th percentile of 56 and a 97th percentile of 62 for fuel model G. When you are implementing this new system in WIMS, you have to go in and define those breakpoints yourself for now. Here's another futuring thing. We stopped deleting data from WIMS. So if you ever remember that WIMS only used to keep 3 years of data, we now are aggregating all of the data and not getting rid of it. We are also going to add back in all the old data, which means that we can tell WIMS to go in and pre-calculate all of the percentiles and populate these things based on breakpoints and update them automatically on a regular interval. That'd be pretty handy. because that don't happen right now. But for now, when you go back and you want to run a fuel model Y on your unit, the only thing you have to do in Fire Family Plus is do a daily frequency table and tell it to give you the 90th and 97th percentile. Does everybody know where that is? You might actually, let me just show you and not assume anything. If you have this set up for fuel model Y and you go to weather climatology and you come down to ERC, you'll notice that CP1 and CP2 are, you can change them. So if you work for the BLM and you want 80th and 95th percentile, you can just key it right in. Or if we want the 90th and 97th, we can do that too. But when you do that, you do this daily frequencies right over here, like so, and you run the new model, which you will get a chance to do this week. And we tell good stories while it does its thing.
I have a question, Matt.
Yeah.
So if,
Who's talking?
this is EJ,
Oh,
if we define our thresholds, say for staffing class, we're using BI, and our staffing level 4 threshold comes out at like the 83rd percentile, that's the number we should put in to WIMS? That
Yeah.
threshold between the beginning of staffing level 4, whatever percentile that comes out to be, and the high end would be whatever the beginning of staffing level 5 percentile comes out to be, if we want WIMS to work for us.
yes. So it doesn't really, so the WIMS asks you to put in the percentile number, but it's completely ignored. There's nowhere where that gets used. The only thing that gets used is the absolute number, and it gets used as that staffing index low and high in those equations. And as soon as you do that, yeah. So here's basically, that was the daily frequency for this station. You can run it for a SIG, set the CPs to whatever you want, and then you get this handy dandy 2 little numbers right there. So all you have to do to make it work, pull those 2 numbers, transpose them over, and key them into WIMS, and Bob's your uncle.